Hi, Algebra 2. In section 6 here, we're going to be looking at inverse functions, determining whether the inverse of a function is in fact a function, and we're going to write rules for the inverses of functions. Here we go. First of all, what is an inverse? That's going to be a function that undoes a different function. So you're going to have a lot of the opposite operations happening. So if you see addition, in the inverse, you're going to see subtraction. In an inverse function, you're going to see that the x and y values are essentially just flipped. The x's become the y's and the y's become the x's. And lastly, the inverse is going to be the reflection of the line across the line y equals x. So I'm going to show you what that means with these two examples here. F of x equals 3x plus 2. This notation right here means the inverse of that. So in function notation, f to the little -1, that just means the inverse. We're not using it as an exponent. So the inverse of function f is going to be x minus 2, notice that's the opposite of addition, divided by 3. That's the opposite of your multiplication. On the graph, I've drawn the line y equals x. It's that perfectly diagonal line through the origin. And then in blue, I've graphed our original function. And I've started with our y-intercept of 2. I've used that slope of 3 to go up 3 over 1 to make new points. In red, I've graphed the inverse function. Now, I did rewrite it as 1/3 x minus 2/3, dividing both of those pieces by 3, because then I could use my y-intercept of -2/3 and then use my slope up 1 over 3 to get my next points. And you can see that our inverse is a reflection of the line, of the blue line over that line y equals x. Here's your step-by-step directions on how to find the inverse of a function. So if we're going to find the inverse of this, f of x equals 7x minus 4, step 1 is to rewrite f of x equals as just y equals. So instead of f of x, we put in y. Then we swap the x and the y. So we switch them here. Remember, an inverse function has x and y switched. So then step 3, we're going to solve for y, getting y by itself. Here's my steps to get y by itself. I end up with this, and then I rewrite it in function notation. So the inverse of f of x is going to be x plus 4 divided by 7. Notice you're going to see the opposite operations here versus what we started with. I started with my original function g of x. I wrote it as y equals. I switched my x and my y, and then here's my steps to get y by itself. I've written it now using function notation, and since I'm going to graph this, I do think it's going to be easier to rewrite it as 1/2 x plus 2.5, because then I can look at my graph. I can start at 2.5 for my y-intercept, and I can use my slope of 1/2, so up 1 over 2, and there will be my graph. To see this a little bit better, I've added our original function g of x in red there. And then here's that line, y equals x, that perfectly diagonal line. And you can see that it really is just a reflection over that line. The other part of the direction was to determine whether it is a function and state its domain and range. Remember, a function can only have one output for every input, and we do see that happening. Linear equations are going to be functions. So its domain and range. In this case, we don't have any restrictions. So our domain is that x can be all reals, and our range is that the y values can be all reals. This function's a little bit different because of the squared. I've rewritten it with y and then flipped my x and my y's around. Change that to a y. And then I need to get y by itself, so I'm going to take the square root of both sides first. When you take the square root of both sides, you do need to be careful that you include the positive and the negative values of x. Here I subtracted 2 from both sides, and then I multiplied both sides by 2 to get x, or to get y by itself. And when you do this, make sure that you multiply everything here by 2, so I just left everything on the left side in parentheses. And then finally, I use a distributive property just to simplify this, and then put that into function notation. So this is going to be the inverse of function f. Now when you graph it, I would definitely sketch this into your notes. Here's our original function, 1/2 x plus 2 the quantity squared, and you see that quadratic that we would expect. Now when we graph the inverse, because we had that plus or minus, Desmos does not have a plus or minus button, so you need to graph the two pieces separately. So here's the positive piece of the function, I'm going to turn that on, and you'll see that it's just half of a parabola. And then the negative piece of that function is right there, and you'll see that's the other half of the parabola. So now you can see that these are going to be a reflection across that line, y equals x, that's our purple line right here. The question was asking us, is the inverse, which is right here, is that a function? No, it is not, because you'll see that it's turned on its side. It has two outputs for each input, and a function can only have one output for each input. So the inverse here is not a function. If we were going to talk about the domain and range, the domain is all your possible x values. Those can only be positive values. You see we don't have any negative x values. Y values can be anything. They're going to range from all the positives to all the negatives. So we just saw an example where the inverse was not a function. When both the function and its inverse are functions, that relation is called a one-to-one function. And in that term, that means that each y value is paired with exactly one x value. You can figure out if something is a one-to-one function by taking the composition of two functions, meaning you take a function of a function. So you're going to do, for example, f of g of x and g of f of x. And if they're both equal to just x, then it is a function. So here I've set up f of g of x and g of f of x to figure out if these two functions are inverses of each other. So here I've started with function g, 3x minus 1, and in the place of x, I've put in the entire function g of x. Here I've started with function g, 1/3 x plus 1, and in place of x, I've put in the entire function f of x. When I simplify f of g of x, I get x plus 2, and when I simplify g of f of x, I get x plus 2/3. These are not equal to just x. If they were functions, they would be equal to just x. So they're not equal to x, so they are not inverses of each other. Since both of these functions, the composition of both of these functions equals x, these two functions are inverses of each other.